Hello everyone. In today's session, we are going to discuss some examples for resolution algorithm. So given certain facts and we want to convert that facts into a predicate logic statement and then convert that into a CNF, then you have to prove a resolution for it. Okay, so these are all the things that you want to do. So what all the facts that is given, like you have a team Delhi, Mumbai, and the final matches between Delhi and Mumbai, and given these are all constant facts. Okay, so there is no variable included, it is all direct facts stating that there is a team named Delhi, there is a team named Mumbai, and there is the final match that is between Delhi and Mumbai, and it is also given that Delhi scores 350 run, Mumbai scores 350 run. Delhi lost 5 wickets, Mumbai lost 7 wickets. So all this facts from A, B, C, D or direct facts. Okay, so these are all your constant value. So you have to directly write it. And when it comes to E, the team that scores the maximum run wins. So here you want to compare two teams, compare the run function of two teams, like the value of run between two teams, and whichever is higher, that team wins. So it is a universal fact. Whenever a cricket match is there, whenever whoever scores the maximum run will be into this winning category. Okay, and so this is a universal fact, so you have to use your universal quantifier here. And F statement also same, like if the scores are same, the team which lost the minimum wicket will win the match. Again, it is an universal quantifier, it is stating about all possibility, like whenever a team plays and if the run is same, then we are going to consider the wicket. The team that which lost the minimum wicket will be winning the game. Okay, so these are all the facts that is given. Now what we have to do is convert these statements into a predicate logic statement. So when I am converting it, I try to use, like from A to D, I try to use a constant values. It is a direct conversion. So when I have this team A, I can write it as, team Delhi, I can write it as team D. And team Mumbai, I can write it as Mumbai is a team. Okay, and the final matches between Delhi and Mumbai, how can we represent it? Final match between, I used D for Delhi, right? D and M. Okay, so the final matches between Delhi and Mumbai. So follow the same scenarios here. When it is between Delhi and Mumbai, write it as D comma M. And D is your scorecard. Okay, so scorecard consists of a team, runs and wickets. So there are 3 parameters into it. So I can use a scorecard like this. In scorecard, I have team Delhi with 350 runs and 5 wickets. Whereas you have one more scorecard, team Mumbai with 350 runs and it lost 7 wickets. Okay, so these are all your facts. It is a direct constant values. Okay, and I'm adding all this into a database. Okay, so what I can do is I'll just give the rule. This is your knowledge base. So I can give some values for the knowledge base. This is my first rule, second rule, third rule, fourth rule, and fifth rule. Okay, so these are all your direct rules that are added. And when I am adding the rules, these are all and connected, right? In my knowledge base, when I am adding a rule, every rule will be in a and connected format. Why it is and connected? Everything is true. Okay, all the facts that are given to us is assumed to be true. So there is a team called Delhi, there is a team called Mumbai, and the final matches between Delhi and Mumbai, and the score of Delhi. So it is all and connected. Everything is true. Got it? So now we had all these rules. Now we are going to go ahead with the universal quantifier. We'll take this E rule. So that will be my 6th rule. And what it says, the team which scores the maximum run will win. And so you have to take a scorecard of 2 teams and we have to compare it. So what we can do is we have the scorecard, and the scorecard variable consists of 3 values inside. So I'm going to use the same. Okay, so I'm going to take this as my scorecard and I can write a rule like for all, we are comparing two teams, right? So I'm going to take X as a team, Y as a team, and I'm going to take the scorecard of first X. X will have a scorecard. The score variable is declared, like the score predicate is declared with three variables inside. One is the team name. So team name is the one that I'm going to put it as a variable. Since the comparison is mainly between the variables, I'm going to add this as a variable here. And we have a value given for this run. For first team, I take it as R1, and we have a wicket also. So when I'm using the variable or the predicate, I have to follow the same structure I have used when I declare the predicates. Okay, a scorecard will consist of three. One is the team name, another one will be the runs that they score, another one will be the wickets. So these are all the things that are given in my fact. I'm going to use the same. Okay, and so I'm going to compare two teams. So first team, you'll have a scorecard that is released, and second team will be your Y team. Okay, I'm going to take X team, Y team, and the scorecard for Y will be again like this: R2, W2. And what is the major constraint that we are going to have? The team that scores the maximum run will be winning. So when R1 is greater than R2, okay, when all this condition satisfies, I'm going to give it as X wins the game. Okay, so X is the first team and the run of X1 is greater than X2. So with this, I'm going to declare that X wins the match. Got it? So this is how we declare a predicate logic statement. We have to take everything into constraint. There are two teams that are playing, and I'm going to compare the scorecard of it. So I have to take both the scorecards, and what is the condition that I'm going to give? I'm going to compare the runs. Okay, so R1 greater than R2, then we can declare that X wins the game. And similarly, I can add a seventh rule stating that if the team with the which has the same runs, then we have to go ahead with wickets. So it is again, you're going to compare two teams. One with the score of, one is team X with the run of R1, wicket of W1. Even though we are just going to compare wickets, the way in which we represent the score should be same. Okay, when you are declaring a predicate, you have to use the same predicates wherever you are using it. Okay, so a score will always consist of a team, run and wicket. So this is your X team, Y team score will have R2, the wicket 2. And what is the condition you're going to have? A team which lost the minimum wickets is going to win the match. So if W1 is less than W2, we can declare X wins the game. Okay, so the first step is done. All the facts that we have taken here are converted into a predicate logic statement. Okay, so next what we have to do is we have to convert this into a CNF, into a conjunctive normal forms, clause forms. So when I'm going to convert this into a CNF structure, what I have to do is, first I have to take a statement that consists of for all and there exist conditions. Okay, so with this bounded variable, we cannot break it directly. So you could have learned it in unification process, right? So whenever you have this bounding, we cannot directly break the bounds. So what I do, I have to make a substitutions here. Okay, so that is your unification process. Only after making a substitution, I'm able to break it and I can convert that into a CNF structure. So what I'm going to do, I'm going to make a substitution. Instead of X and Y, I'm going to have a values for X, value for Y, and what value we have to give here, that should be reflected from what I have already. Okay, so how I'm going to break for all denotes, it is for all the conditions, it is for all the teams. Since this X and Y is going to denote all the teams, I have two teams that is given to me. I have team Delhi and team Mumbai. So I have to substitute. Wherever X comes, I am going to substitute D. Wherever your Y comes, I'm going to substitute it as Mumbai. Okay, so it is up to you. You can make your choice. Okay, this is easy for me to declare. Since I want to declare that Delhi wins, I'm going to take X as Delhi. Okay, so win has a variable as X. So I'm going to declare X as Delhi. So this is your substitution value. So X I'm going to substitute it as Delhi and Y I'm going to substitute it as Mumbai. Now we can break this for all. Why we can break this for all? Since we are making the substitution. Now it is particularly for the given scenario I'm going to write it. It is not for all condition. It is specifically for Team Delhi with this 350 runs and 5 wickets and Team Mumbai with this 350 runs and 7 wickets. I'm going to write the rule. So this is a unified rule only for the given facts. So how can I write the rule? So this sixth rule I'm going to modify it as score of Delhi is 350 with 5 wickets and score of Mumbai is 350 with 7 wickets. And when I'm going to compare the run value, I'm going to take these values directly since the values are already given. So R1 is 350 greater than R2 is also 350 implies Delhi wins the game. So this is the rule that we are going to form here. Got it? Now the next rule is, again I'm going to repeat the same by applying X as Delhi, Y as Mumbai. So I can rewrite this rule also as score of X. I'm sorry, it is not score of X. The first team is Delhi. I'm going to compare score of 350 with 5 wickets and score of Mumbai with 350 runs and 7 wickets. And here we are going to compare the wickets. Okay, so what all the wickets I have? 5 less than 7 implies Delhi wins the game. Got it? Now we have broken this universal quantifier and we have made a substitution and we make a unique statement just for, made a unique statement just for this. Okay, so now unification is done. We need to convert that into a CNF structure. So what is a CNF structure here? When I write a CNF structure, everything is AND connected and this implies and all need to be removed. And how you're going to remove this implies? So when I have the statement as P implies Q, I have to write it as negation P or Q. Right? So this is the statement that we are going to write here. So what I can do is, like, I'll do it with the resolution algorithm first. So that is what is asked. See, you have to prove it by a resolution. You have to use a resolution algorithm for it. And I'll also give you a shortcut for verification too. Got it? So what I do, I'll just write all the rules again here, and that is your final negated rules. Like I'll take it negated rules and I'll just copy the rules later. So I'll take the sixth rule, and sixth rule is your implies condition. And what does this implies condition means? When you have the statement of P implies Q, I can write it as negation P or Q. Okay, it is all conjunctive normal form. All the literals are connected using and inside each and every rule it should be or connected. Got it? So what I'm going to do, I'm going to negate this complete structure. It is negation of score of this and score of this and your run or wins of D. Got it? So I haven't copied all as it is. So it is your D score, M score, and this is your run connections. Okay, comparing the run. Now when I have a negation of some statements, okay, and what I have to do, it is all AND connected, and you have there is no one unique literal over here. So what I can do, I can bring this negation inside using De Morgan's law. When you are bringing a negation, how can you write the rule? So negation of P and Q can be written as negation P or negation Q. I'm going to follow the same. Now I rewrite this rule as negation of score of, I can write it as direct score. I don't want this. Negation of score of D 350 and 5, or negation of score of Mumbai 350, this 7, or 350 greater than 350, or wins of D. Okay, so this is the broken rule of 6th. When I want to convert, this is the converted rule. I have removed this implies, converted that into a single literal, that is all or connected. Okay, now similarly I have to do it for the 7th rule also. When I am doing it for 7th rule, it will become, again, directly make a substitution. Okay, it follows the same structure. So I can write it as negation of score of D 350, 5, or negation of score of M 357, or I'm comparing 5 greater than 7. So this is all negated. Okay, I'm sorry, this is all negated. Negation of 5 less than 7, or wins of Delhi. Okay, now I have all unique rules. See, Team Delhi is a constant. Mumbai, final matches between Team Delhi, Mumbai, and the scorecard, 2 scorecards. And these rules, all the rules are all right now in a conjunctive normal form. Now these are all the final rules that we got out of your given conversion. After converting it into a CNF structure, this is the rule that we have it. Team Delhi, Team Mumbai, final matches between Delhi and Mumbai. This is the scorecard of Delhi, Mumbai. And the 6th rule, 7th rule, that is converted into a conjunctive normal form. So what we have to do, you have to use a resolution algorithm. So what we have done is converted the statement into predicate, and that is again converted into the CNF structure. And finally, we want to prove that Delhi wins the match. So there is a given condition. So you want to take this statement. So how can you write a predicate logic statement for Delhi wins? So wins of Delhi, right? That is the statement that we have used. So I have to take that statement. That is the final thing that we want to prove. So this is the 8th one. You're going to add a new rule. And that new rule is, you want to add the rule as Delhi wins the game. This is what we want to prove. Okay, so this is the resolution that we want to prove. What we do is, we take the negation of it. It is proof by contradiction method. So what is proof by contradiction method? We take the condition, whatever is the condition given, we take the reverse of it and we try to add it into a knowledge base. We try to prove that as false condition. Okay, now what we have to do, you have to write the rules directly. Now next step is to draw the resolution graph. So when you are drawing a resolution graph, first we have to make sure that since we already know that this condition is not going to work. Okay, so this is the first condition that we want to get checked for satisfaction. We want to compare the runs, and we already know that the runs are same. We are not going to take this rule. Okay, so what I do, I take this rule directly. I'll start from here on. Okay, so the given, I'm going to do the resolution graph. I start with this rule. Since this is not satisfied, I'm going to ignore this rule directly, and I have to take this negation score of Delhi 355, or negation score of Mumbai 350 with 7 wickets, or negation 5 less than 7, or wins of Delhi. Okay, so this is all the rule that I have taken here. What we have to do, we have to use the existing rule, we have to compare it, and we have to make sure that it is all nullifying. See, it is given that the score of Delhi is 355 and that is not. Okay, but exactly in your rule 4, we have that the score of Delhi is 350 with 5 wickets. It is true. When I compare these two statements, these two will get cancelled off. I cannot have a rule that consists of negation and the negation of a predicate and the predicate into my knowledge base as it is. It is not possible. Okay, and it is all or connected. What is meaning of or connected? Need not everything to be true. So sometimes we have a false statement too. So it says that the scorecard of Delhi is 355, it is a proven logic, it is correct. So we cannot have a negation of it. So finally, we want to check whether negation of scorecard of Mumbai is 350 and 7, or negation of 5 less than 7, or wins of Delhi. So after cancelling this is for all the predicates that I have. Now I have to compare it with rule 5. Rule 5 consists of scorecard of team Mumbai, and the scorecard of team Mumbai is 350 and 7. So I cannot have a statement of these two in the same. A predicate and its negation cannot be there. Okay, either any one will be true. So with that, I am left with only one choice of proving 5 less than 7 or wins of Delhi. And by the known fact, I'm sorry, this is your less than 7. By the known fact, we know that 5 is less than 7. Okay, so we cannot have a negation of that statement. It is not possible. Okay, so 5 is strictly less than 7. 5 is strictly less than 7. This is true. Okay, I cannot have a negation of it. It is not possible. So the left out statement is wins of Delhi. And out of the statements, we already have taken this 8th statement as negation wins of Delhi. So this is the resolution that I want to prove. But in my database, I have negated it and add it over here. So when I negate it, I cannot have Delhi wins and Delhi doesn't wins into the same place. Okay, so it is getting nullified. What is the meaning of nullification? When something goes into a nullified pattern, it means that the assumption that we have taken is false. What is the assumption that we have taken? Here the assumption that we made is negation of wins of Delhi. So this is wrong. Hence, we want to prove that Delhi wins the game. Okay, so this is how a resolution algorithm actually works. Okay, so I hope you understand how to draw this resolution graph. These are all the steps that are involved in. First, whatever is given, you have to write its corresponding predicate statements. And we want to convert that predicate statements into a CNF structure like this. And then you have to use a resolution graph. Okay, so that is another way you can solve it. But that is like a kind of connecting it on like without going ahead with your resolutions and without going into your CNF structure, what we can do is we can connect everything in online, everything in and connected. See, I know that scorecard is this and scorecard of Mumbai is this. So in my 7th rule, this is done. And we already know that by proven fact that 5 is always less than 7. So I can add all this into my rule base and I can use a modus ponens rule. Okay, since everything is AND connected, I can combine everything into a AND using AND insertion function. And by using that and this rule, I can declare it as Delhi wins using your modus ponens rules. That is a simple way of doing it. But when it is asked us to prove using resolution algorithm, you have to follow the steps. Okay, thank you.